All right, so today we have Elias Furrer, who will tell us about the 3D A model and generalized symmetries. Take it away.
Thank you so much for the introduction, and also thank you to the organizers for the invitation to give this talk. So today I'd like to report on some recent and ongoing work in collaboration with the group from University of Birmingham. So that's Cyril Klosse, Adam Keyes, and Osama Clave. So this talk is based on two papers. One paper, most of the talk will be based on the paper from the first paper here from last year, and then also the last part of the talk will be show some results from a more recent paper from January this year. So as you can see, in this talk, I will discuss these generalized symmetries in the context of this 3D A model. But before I explain to you what they precisely mean by that, let me give you some motivation. So one reason why we like to study supersymmetric QFTs is because they often allow us to study phases analytically and exactly, in particular, strong coupling. So this often requires replacing our Euclidean spacetime by some d-dimensional manifold. So this could be compact or non-compact. So there are various techniques available, such as, for example, the omega background, or we can also consider some d-dimensional smooth and compact manifold, such as, for example, the sphere. In this talk, I'll focus on 3D n=2 theories on so-called Seifert manifolds, for which many results from the literature are available. But then at the same time, our understanding of notions of symmetries has been drastically extended since this foundational work by Gaiotto, Kabustin, Seiberg, Willett from more than 10 years ago, where the ordinary notion of global symmetry in QFT has been extended to higher form symmetries and higher groups and non-invertible symmetries and categorical symmetries and so on. So really the point is that we want to use all the techniques available to study 3D n=2 theories and to study analytically and exactly the effect of generalized symmetries, and in particular in the context of compactifications. So the plan of the talk is, first I will give you some reminder of or some small introduction to this 3D A model. Then the main part of the talk will be to study higher form symmetries in this 3D A model. So I will discuss how these higher form symmetries act on the supersymmetric vacua of the theory, how it organizes it, what is the effect of anomalies, and so on, how we can compute insertions or expectation values of line operators, and how we can use it to compute, say, partition functions of theories that differ by the global forms of the gauge group. And so one particularly interesting example that I will discuss in some more detail is the SUA Chern-Simons theory, which has a quite rich structure of symmetries. And then in the last part of the talk, I will extend this discussion to arbitrary Seifert manifolds. So let me start by introducing this 3D A model. So we consider always 3D n=2 supersymmetric gauge theory. So this can be in particular Chern-Simons theory, possibly coupled to matter, based on a gauge group G tilde, which is a product of simply connected Lie groups or of unitary gauge groups on some space that's a two-dimensional surface sigma times S1. The 3D n=2 half-BPS backgrounds on which we can place these theories are the Seifert manifolds. And so the simplest case of this is just, say, a 3 torus or a product space where we have a closed genus G Riemann surface times a circle. From each such 3D n=2 theory, we can compute or study this 3D A model. So what we want to do is we take this 3D theory T or tau, and we put it on a circle, after which we get a two-dimensional n equal to 2,2 supersymmetric theory. And from this theory, we can compute or obtain the topological A-twist. And so it becomes really a two-dimensional topological QFT. In the 2D n equal to 2,2 language, the vector multiplet is repackaged into a twisted chiral multiplet whose lowest component is the complex scalar U. So we have this complex scalar is combined or is written in terms of the real scalar sigma, which combines with the 3D gauge field along the circle direction. And so this gives us the 2D Coulomb branch parameter, where beta is the radius of the S1 circle. So this Coulomb branch parameter generically is valued in Cartan subalgebra of the Lie group. And so when we have a non-abelian group, this is useful to expand in terms of components. So we take the basis of the Cartan subalgebra, and what we really want to look at are these coordinates with respect to the basis. This 3D A model has two very important characteristic functions that essentially control the whole theory. So the first function is this effective twisted superpotential, which determines the supersymmetric ground states. So I'm not writing down the exact formulas, but this can be obtained. And so this function here obtains contributions from, say, the Chern-Simons action, but then also from chiral multiplets, so any matter contributions. And the other function is the effective dilaton omega, which obtains also contributions from the W bosons if we have a non-abelian gauge group. And it's obtained by integrating out the charged massive chiral multiplets. And so what it does is it couples the Coulomb branch parameter to the curvature of sigma. And then the point is really that the low energy dynamics of this 2D TQFT is completely encoded in just these two functions. And now how to see how that's the case. Really, the punchline is the supersymmetric partition functions for this theory tau can be computed in this 3D A model as a trace over Hilbert space of certain operators built out of these two functions, the twisted superpotential and the effective dilaton. For this, we need to introduce a new function from the effective twisted superpotential called the gauge flux operator. So for each component in the Cartan subalgebra, we compute the derivative of the twisted superpotential with respect to the coordinate. And then it turns out that the supersymmetric ground states of the effective 2D theory are the critical points, which we denote by U hat of the superpotential. And we call them the beta vacua. And so how we do this in practice is we start with all the Coulomb branch parameters, which lie in the Cartan subalgebra. We mod out by this magnetic weight lattice of the group G tilde, which essentially encodes the large gauge transformations. The solutions for the ground states are the Coulomb branch parameters such that the gauge flux operator evaluates for each component to 1. Then we want to disregard any putative solutions which are not acted on freely by the wild group, which I denote by WG tilde. And at the end, we want to identify points or solutions which are identified or which are related by the wild group. I'll show this in an example a bit later. And then so what we can do is also that the beta vacua give us a basis of the S1 Hilbert space. So for each beta vacua U hat, we associate one state in the Hilbert space, and the S1 Hilbert space is just the linear or the complex span of these states. And then to describe the or to compute partition functions, say on some genus G Riemann surface, we need the Handel-Gluing operator. And this is built out of the effective dilaton, the exponentiated dilaton, and the Hessian matrix of the twisted superpotential. And what it does if we add this Handel-Gluing operator to the partition function is that it accounts for increasing the genus of the surface by 1, and therefore adding a handle to the surface. Now we can compute the topologically twisted index. So what it is it's a trace over the Hilbert space of the theory compactified on sigma G with a topological A twist. And so it becomes really a trace over this Hilbert space with the term number inserted. But how to compute it in the A-model formalism is really that it becomes a trace over the S1 Hilbert space, where instead we add in a Handel-Gluing operator raised to the G minus 1, where G is the genus of the Riemann surface. And so this becomes this finite sum over the Bethe vacua, where we evaluate the Handel-Gluing operator. So the simplest example of this twisted index is just the Witten index, where G is equal to 1. So we look at the partition function on the 3 torus. And then this twisted index can also be computed by basic surgery operations on sigma. So we can describe the Riemann surface in terms of cap and cylinder and pair of pans. And we can associate these 3 components in terms of operators on the Hilbert space. And so we can put together any genus G Riemann surface. As an example, to demonstrate this, we can look at pure Chern-Simons theory based on a simply connected Lie group G tilde. So the twisted superpotential is just given by this simple formula, where here we contract essentially using the killing form. It turns out that in this case the beta are in 1-to-1 correspondence with level K integrable representations of the same group, but where we shift the Chern-Simons level by the dual Coxeter number of G. And then so given any such integrable representation with weight lambda, we shift it with the Weyl vector of G and contract it with the inverse killing form matrix. And this gives us solutions to the Bethe equations. And also we can write down explicitly what is the Handel-Gluing operator. So it turns out to be a function of this column branch parameter, which is k to the rank of the Lie group times the determinant of the killing form matrix, and then we have a product over all the roots of the Lie algebra. And to give you a more concrete example, we can just look at say SU2 Chern-Simons theory. So in that case, the Cartesian subalgebra is just one-dimensional, and the twisted superpotential is just literally k times u squared. So we can write down the Bethe equations, from which we can just read off that all the possible solutions have to take this form, which is just an integer L divided by 2k. But L can be any integer. But then we need also to mod out by large gauge transformations, which identify u with u plus 1. And so we can only keep a specific choice of our integers L. But then next we also have the Weyl group, which maps u to minus u. And so in particular, we have a fixed point under that Weyl group, which we want to disregard, which is say L equal to 0. And then we want to finally identify also solutions related by the Weyl symmetry. And so at the end, we end up with these particular values for L from 1 to k minus 1. So this gives us k minus 1 numbers, which turn out to be the k minus 1 vacua of the SU2 level K theory. And so that's also the Witten index of the 2 level K Chern-Simons theory. If you want to study the partition function on a genus G surface, we need to compute the handle-gluing operator, which turns out to be just given by this simple sine squared function. And so the twisted index becomes the sum over the bit vacua of the handle-gluing operator raised to the G minus 1. And so it just is given by this formula here. And up to this shift of the Chern-Simons level, this is just the well-known Verlinde formula for the pure SU2 level K Chern-Simons theory. And so it famously counts the number of conformal blocks of the same SU2 level K Witten model. So this is an integer. Now, let me also tell you a bit more about how the one-form symmetries appear in this 3D M model. So, but before I do that, maybe I should remind you a little bit about some important aspects of generalized symmetries. So as been discussed in this important paper from 2014, we can, instead of having ordinary global symmetries, we can consider P-form global symmetries, which I denote by gamma P, and it corresponds to charged operators of space-time dimension P. So for example, Wilson lines or surface defects and so on. So for an ordinary or zero-form symmetry on some d-dimensional space, we can associate a background flat connection for that symmetry, which defines as some element in H1 valued in gamma 0. And so this generalizes to a P-form symmetry in that we can couple the symmetry to background fields, which essentially assigns us holonomies valued in the gamma P to P+1 dimensional cycles. This P-form symmetry we can implement by symmetry or charge operators, which for each element in the P-form symmetry group gives us an operator based on a codimension P+1 closed manifold. And now the important part is also that we can consider gauging this symmetry. So we couple the symmetry to a background field, and then we promote that background field to a dynamical field. So we want to sum over these fields. And this gives us the partition function of the gauged theory. So we sum over these dynamical background fields. And we can also couple to background fields here for the dual symmetry that appears when we gauge it. Now let's see how this plays a role in the A model. So the reason why we want to study it is because this bit vacua formula, which is very nice, where we can just sum over bit vacua to compute partition functions. This only works for 3D theories where the gauge group is either simply connected or unitary. So it could be, for example, UN or SUN, but it's not. It doesn't work for, say, PSUN or SON. So what we want to do is to study the action of one-form symmetries in the 3D A model and also its gauging. So we start again with a 3D n = 2 theory, where we have a discrete one-form symmetry group in 3 dimensions.
What's the thing that doesn't work with the formulism? Is it simple to say? Like for PSUN, for example. Why is the simply connectedness important?
I guess one thing you can see is that everything we do goes directly to the Lie group, but then the Lie group doesn't care about the global form, and so we need to
the Lie algebra. You mean?
Sorry, the Lie algebra, not the Lie group. Yes.
I see. Okay. I see. So
yes. So we need to, in a sense, go.
So it gives you one
back
answer
to the simply
and it
connected.
corresponds to the. I see. Yeah. Okay. Thanks.
So again, we start with the 3D n = 2 theory, which has a discrete one-form symmetry group, which is, say, a subgroup of the center of the gauge group. So this could be a Chern-Simons theory based on G tilde being SUN or spin n or SPN, or even just the exceptional group E6 or E7, which have center symmetries. and possibly coupled to adjoint matter. And then in 3 dimensions, the operators charged under the one-form symmetry are topological line operators, so in particular Wilson lines. But then in 2 dimension, in this 2-dimensional description, the symmetry gamma manifests itself as 2 symmetries. So we get a copy of a one-form symmetry and a copy of a zero-form symmetry, which both are isomorphic to gamma itself, the group we start with. And the one-form symmetry is generated by topological point operators, which arise from 3D lines wrapping the extra circle direction. So from the 2D prescription, it looks like a point, which is what is the defect for a one-form symmetry in 2D. And at the same time, the zero-form symmetry is generated by topological lines with support on 1 cycles on the Riemann surface here on the cylinder. And so again, it looks like a line from the 2D perspective. And so it's a one-form symmetry. Sorry, a zero-form symmetry. And so what we want to do is to study the action of these 2D symmetries, the zero and the one-form symmetry on the Hilbert space. It has been known that in general 2D TQFTs, that one-form symmetries acts diagonally, whilst the zero-form symmetry acts by permutations. So let's look at the action of the one-form symmetry first. If we insert a 3D topological line along the S1, the S1 circle, this essentially amounts to inserting a background G bundle over sigma, which is not the G tilde bundle. And so these fluxes are really in the magnetic white lattice, where the magnetic white lattice for G, as in G tilde mod, where we quotient by the center symmetry, is a larger or more finer lattice than the G tilde lattice, the one for the simply connected group. And it is a larger lattice in precisely the way that the quotient is isomorphic to the group we start with. And then in the A model, this topological point operator accounts for this flux by being a flux operator. And so the one-form symmetry acts in this way by having, in a sense, a fractional flux. So we evaluate this flux operator, but we contract it in a sense with the group element gamma. So for example, if our capital gamma is a Zn subgroup, this gives us some Zn phases that it acts with. And one particular or important notion is also that whenever we have a one-form symmetry in 2 dimensions, this gives us a decomposition of the theory into a direct sum. And so which are also, the components are also called universes. And so in particular, also it decomposes our set of Bethe vacua or the Hilbert space into sectors, which are abstractly labeled by the Bontrager dual of the one-form symmetry. But it is really just the charge under the flux operator. Now, how we gauge the symmetry, the one-form symmetry, is in general for a p-form symmetry, we can either sum over background fields, or we can also sum over insertion of the topological operators. It's in a sense dual by concurrent duality. So for example, we can insert the one-form symmetry operator pi gamma by just inserting it literally into the sum. And then if we want to gauge the one-form symmetry, we just sum over all the elements gamma in capital gamma with some normalization. And then what it actually does is just it projects us to one particular component of the decomposition. So gauging one-form symmetries is really undoing this decomposition that the one-form symmetry provides. And this doing so by projecting us to a specific sector in the theory. Now the action of the zero-form symmetry and the Hilbert space is also interesting. We can look at the topological line operators wrapping the cylinder which turns out to act as the center symmetry. So it maps essentially a Coulomb branch parameter U to U plus gamma. And so one can show that if U is a bit vacuum, then also U plus gamma is a bit vacuum. And so what this is really is just a permutation of bit vacua. And now we have a zero form symmetry acting by permutation on the finite set of bit vacua. So we can look at orbits, which are denoted by omega hat under the zero form symmetry. We can also consider inserting the topological line along the time direction on the cylinder. And then in analogy with doing orbifolds, say, this should protect us to, or this should give us twisted sectors. And so in the presence of these lines, we have the twisted sector ground states, which I denote in this way. And they are just the bit vacua, which are satisfied, which have some non-trivial stabilizer. And before I show you how to gauge both of the zero and one form symmetries together, we need to look also at anomalies and how they affect the vacuum structure. So the 3D one form symmetry can have a non-trivial Hooft anomaly, and that's special to 3 dimensions, which is because the topological lines in 3 dimensions can themselves be charged under the one form symmetry. In the 2D description on sigma, this Hooft anomaly is realized as a mixed anomaly between the one form and the zero form symmetry. And it arises basically because the one form symmetry operators, pi gamma, can be charged under the zero form symmetry and vice versa. And so it turns out these operators become non-commutative as operators on the Hilbert space. And they are non-commutative in a precise fashion. So we can compute this or introduce this anomaly factor curly A, which depends on the group elements for the zero and one form symmetry. And it can be computed just from the effective twisted superpotential as some derivative and then some shift with respect to gamma zero. And this anomaly factor actually only depends on the Chern-Simons levels of the gauge theory. And it turns out to constrain the vacuum structure in an interesting way. So in order to see how it does so, we can introduce homomorphism phi A, which takes an element gamma in capital gamma zero in the zero form symmetry group, and it maps it to this exponentiated anomaly factor. In 2 dimensions, the one form symmetry is always preserved by the vacua, but the zero form symmetry is generically spontaneously broken to a subgroup, which is just the stabilizer of the vacuum under the zero form symmetry. The kernel of this homomorphism turns out to dictate the orbit sizes that can appear in this story. So the stabilizer of each orbit is some subgroup, say of gamma zero, and it turns out it has to be a subgroup of the kernel of this homomorphism. And if you have some vacuum which has a stabilizer stab U, that corresponds to an orbit of size this, which is just the orbit stabilizer theorem. So let's see what that does in practice. So we can look at, for example, the 2 maximal cases. For example, if you have maximal anomaly, meaning that this factor is essentially always not equal to 1. So the operators almost never compute, except if you have trivial insertions. So then this kernel is trivial. And so any possible subgroup of the trivial group is just trivial. But then the orbits are also of length of the order of the group gamma zero. And that's also exactly the maximum length of the orbit. And so in the fully anomalous case, all the orbits are of length mod gamma zero. On the other hand, if we have a theory that has no anomaly, the kernel of this homomorphism is the full group. And so the stabilizer can be any subgroup of the full group. So in particular, if we have a vacuum where the stabilizer is the full group, that means that the length of the orbit is 1. But the length of the orbit being 1 means it's in a fixed point under the gamma zero group. And why that's is important is because essentially, if you want to gauge this zero form symmetry, we need to count fixed points, and so it's important to be able to enumerate these fixed points. In general, for a genus G surface, we can wrap these topological line operators on the base along any generator of the sigma G. So we have in principle 2G insertions along the base. And again, this is equivalent to turning on background gauge fields for the zero form symmetry. We can associate with these diagrams here the action where we insert these topological lines. And then for arbitrary genus G, the expectation value of the generic insertion just evaluates to the Handel-Klung operator evaluated at all the beta vacua, but not at all the beta vacua, but only those fixed by all of the elements gamma simultaneously. And this gives us a way to compute the twisted index, namely for the G equal to G tilde mod gamma theory. So if we sum over all the insertions, say on sigma G times S1, we have 1 insertion for the S1, and then we have 2G insertions for the sigma G. We normalize it by this factor here, and this gives us the twisted index for the non-simply connected theory. And we can write this as a trace again as before over some new Hilbert space and of some new Handel-Klung operator. So this gauged Hilbert space, the Hilbert space of the gauge theory, can be written as follows. So we label the elements by orbits omega hat, which are orbits under the zero form symmetry, where we select a particular sector from the one form gauging. But then for each orbit that has a non-trivial stabilizer, we add these elements in the stabilizer group. And then the Handel-Klung operator for the G theory can be obtained from the Handel-Klung operator of the G tilde theory by a simple normalization with respect to the length of the orbit that we look at. So that was all slightly abstract, but it does work very generically. But maybe to demonstrate that it does work correctly, and also to be slightly more precise, we can look at a specific example. So I like this SUN Chern-Simons theory because SUN has a center which is Zn, and Zn itself can have non-trivial subgroups. So there's quite the rich pattern of gaugings we can study. So for SUN, we can look at, for example, SUN mod ZR, where R is a divisor of N. So these are the possible gaugings that make sense. This N equal to 2 SUN Chern-Simons theory, it flows to bosonic SUN Chern-Simons theory in the IR, where we integrate out the gauginos, and then what happens is that it just gives this shift of the Chern-Simons level. And so as before, we can label the beta vacua for this pure Chern-Simons theory with the topological lines in this infrared TQFT. So for SUN, we can use, say, the Dinkin labels, which are just this n-1 tuple. And then the integrability condition takes this particular form. So we want to enumerate all the tuples lambda1 to lambda n-1, which satisfies this integrability condition. And the number of those you can easily compute, and it's the binomial k-1 choose n-1. And so that's the Witten index, as has been computed by Witten in '99. the SUN level K theory. So the partition function on T3. And now the question one can ask is, how does this 3D one-form symmetry set then organize the Pitted vacua? And what is the, can we consider the gauging of some arbitrary set R subgroup? The gauging of the zero and one-form symmetries we can look at now. So let's start with the one-form symmetry. I denote by gamma 0 a generator of this set n subgroup. Of this set n one-form symmetry group. The set n one-form symmetry charge of a vacuum is given by essentially an nth root of the flux operator. And so it evaluates to this phase. So where n of lambda is the anality of the representation lambda, which labels our Pitted vacua. So if you write it in terms of Young tableau, for example, that's the number of boxes in the Young tableau. And if you want to gauge this set n one-form symmetry, we sum over these elements gamma 0 here. And so this just becomes a geometric sum, and we project to the sector where this anality is 0 mod n. Then the 2D zero form symmetry acts on the Dynkin labels by, in a sense, some permutation in this way here. So I just wrote down a simple example for, say, SU3 level 6. We have 10 vacua, and I just randomly label these 10 vacua by the numbers from 1 to 10. It turns out in this case, there are 3 orbits of size 3, and then there's 1 orbit of size 1, which is a fixed point of this theory. And again, why these fixed points are important is because we want to wrap a topological line along a curve on the base torus, and so this counts the fixed points under this element. And so we want to ask ourselves, can we compute this number? It turns out that the number of fixed points under set n, it depends quite intricately on the arithmetics of the number n and also of the anomaly of the SUN theory, which I'll explain on the next slide. We can prove using this enumeration of the vacua that for all values of n and k, the generator gamma 0 of set n, there is exactly 1 fixed point of the SUN level K theory under the generator if k is a multiple of n, and there's no fixed points otherwise. In general, we also need to know what are the fixed points under an arbitrary element of the set n subgroup. So we can label the elements of set n by small n times gamma 0, where n is just an integer running from 0 to n minus 1. So we label the elements of set n. And it turns out that this element, it generates a cyclic subgroup of order d of n, where d of n is just this ratio n divided by GD of small n and capital N. And with this, we can find what are the number of fixed points under this particular element of set n. And it turns out we can again write it as a binomial factor in this way. But before we can actually study the whole gauging, we need to discuss also the anomalies in detail of the theory. So this SUN theory has a set n one-form symmetry, and it actually has 2 distinct anomalies depending on the values of n and k. One is a pure 't Hooft anomaly, which prevents us to gauge the full set n symmetry. So it is actually known that this SUN, the set R quotient of the SUN theory, only exists if this ratio here is an integer. In the 3DA model, this pure 't Hooft anomaly descends to a mixed anomaly between the 2D zero form and one form symmetry. We can compute explicitly this anomaly factor that I introduced before. And you can see just it depends on the Chern-Simons level for given rank. And why this is important is because we want to sum over all possible insertions, say on the torus or in the sigma t times S1. But when the anomaly factor is not 0, then these mixed expectation values just vanish. And so that obstructs us from gauging both at the same time. And we can also see that this anomaly factor knows about the pure anomaly in 3D, in that if we choose these group elements M and N such that they generate a set R subgroup, the anomaly factor evaluates to this factor here, and that factor is that rational number. That rational number is an integer if and only if this set R quotient makes sense. Now we can assume that, or we assume that this set R subgroup is non-anomalous, meaning again that this ratio here is an integer. And so on top of that anomaly from before, but which we eliminate now, the SUN theory has a mixed anomaly between gravity and the one-form symmetry, which is set 2 valued. So this anomaly in 3D has a known anomaly theory in 4D, which takes this form here, where the coefficient depends on the level and the rank, and then of the R that we want to, of the set R we want to gauge. This anomaly coefficient H turns out to be a half integer if we assume that the set R one-form symmetry is non-anomalous, and it's 1/2 if R is even, and at the same time this ratio here is odd, and it's 0 otherwise. And the reason why that's important is because when H is a half integer, the set R, the generator of the set R one-form symmetry in the infrared bosonic TQFT has a half integer topological spin, and the n equal to 0 or the non-supersymmetric SUN mod set R symmetry is a spin TQFT rather than a bosonic TQFT. And that's precisely the case when this anomaly coefficient is a half integer. And also we can see this from the S3DA model in that this mixed anomaly in 3D takes the form of a modular anomaly on the torus. So if we consider the mixed insertion of the one-form symmetry and zero-form symmetry operators, we can map this back to a single insertion of a zero-form symmetry operator, but only at the cost of a relative sign. And that sign is equal to -1 if and only if the mixed anomaly exists. Now what we want to do is to compute this PSUN Witten index. So we have SUN mod set n at level k. We want to look at first the case where k is a multiple of n. And we want to compute this PSUN Witten index. So we sum over all the elements in set n, where we have insertion along all of the 3 circles on T3. Let's consider first gauging the set n zero-form symmetry on the 2 torus. So if you have 2 insertions, we just need to count the fixed points under both the 2 insertions. So we have 2 group elements and then prime, and we want to count the fixed points. So that's the formula I showed you before in terms of the binomial coefficients. But we want to express this not as a sum over group elements, but actually just the sum over subgroups of set n. And so the subgroups of n are labeled by divisors of n, divisors d of n. And so we need to count pairs of elements in set n such that essentially they both lie in a common set d subgroup. That enumerating function is known as Jordan's totient function, J2. And so that expression from above just evaluates to a divisor sum, so a sum over divisors d of n. And yeah, so this Jordan torsion function can be defined as a product over divisors of d. And the first one, the J1, is also known as Euler's totient function, which might be more familiar. Now we can compute this actually for arbitrary n to gauge also the one-form symmetry, where n is k is a multiple of n, and then including this modular anomaly in T3, which introduces some relative minus signs, we can refine the symbol or the Jordan torsion function J3, which under some conditions we need to insert a factor of 1/7. And then we claim that the PSUN Witten index is given by this divisor sum, where we have this coefficient function, which is this curly J quotient function. So this might be hard to see why that's an integer, but maybe I'm able to convince you by just showing you the first 10 by 10 entries for that, because it's easy to compute. But in general, we don't have a mathematical proof to show that this object here on the right-hand side is an integer. But for example, if n is prime, we can actually prove that this is an integer, which is due to some number theoretic identity from over 100 years ago. We can also generalize it to, say, a set R gauging of SUN, and the result becomes just slightly modified in terms of a divisor sum or a sum over divisors of R rather than divisors of N. And this slightly refines this J3 symbol as well. And at the same, very similarly, we can compute also the Witten index, where we have more insertions along the base. And we can write this again as a divisor sum using this J2G symbol, where we sum over the set T fixed points in this particular sector. And then we just have the handle-closing operator. And so there have been several partial results on this. In particular, this result by Boville from '96, where it was computed for n prime. And there's also some more mathematical works, which, however, mostly studied the case where n is odd, where this mixed anomaly doesn't appear. And so maybe just very quickly to see why, to give you some more check why we can be more confident about this result, is actually because we can check this the result numerically by computing the gauging of the one-form symmetry from this TQFT perspective in the IR. And so the gauging in this perspective is known as anyon condensation, and it corresponds to on the Witten model, it corresponds to extensions by simple currents. In a 3D TQFT, the objects are these anyons, which have two operations known as braiding and fusion. If you have such a one-form symmetry, that means we have a billion anyon, which is characterized by the fact that the fusion with this anyon with all other anyons gives a single anyon rather than a sum over multiple anyons. And so just very briefly for SUN, we can compute this braiding phase, and also the fusion with the anyon with other lines is just according to fusion rules. And then this abelian anyon condensation is a three-step procedure. So in the first step, we just select the set then neutral lines according to braiding with A. So we select these particular lines. In the second step, we identify all lines which are obtained by fusion with A. And in the third step, we take copies of the fixed points. And you can simply put this on Mathematica, and we checked that in all cases, we were able to compute this. It agrees with our formula for the Witten index of SUN mod ZR up to this, including this relative shift of the Chern-Simons levels. And the reason why that actually makes sense that it's the same is because that anyon condensation is essentially the same procedure as counting the states in the gauge Hilbert space. So the first step is essentially just computing the 2D one-form gauging. The second and third steps together is the zero-form gauging, where in the second step we just collapse orbits to single points. So we just consider orbits rather than all of the elements that the orbits consist of. And then if an orbit has a non-trivial stabilizer, we take also copies of that. So we include the twisted sectors. So I guess I don't have too much time left, but maybe let me just say a few words about how we can generalize this to from, say, sigma g times S1 to arbitrary Seifert manifolds. So again, the most general set of half-BPS geometries on which we can place these 3D n equal to 2 field theories are these Seifert manifolds. So they are circle vibrations over a two-dimensional orbifold sigma hat. In principle, we can compute the supersymmetric path integral on this background using supersymmetric localization. But in practice, this is actually only feasible if the manifold has a relatively simple topology, such as the case we looked at now, which is this product space, but also lens spaces and three-sphere and squashed three-sphere and so on. It turns out that this 3D model approach is actually quite powerful in a sense that we can include geometry changing operators which correspond to changing the details of the Seifert vibration. And so instead of computing the partition function on the Seifert manifold, we compute a expectation value or a partition function of on say this sigma g times S1, but we include an operator that changes the details of the vibration. And as before, half-BPS observables can always be computed as traces over Petri vacua. And so this has been completed for unitary and simply connected gauge groups in this paper here from 2018. And what was the task to do was to extend this again to non-simply connected gauge groups by gauging the center symmetries. And in practice, what that means is obtaining what that geometry changing operator means in the gauged theory, so in the G theory coming from a G tilde theory. So very quickly, the Seifert three-manifold is a circle bundle over an orbifold. So we have some S1 vibration over this sigma hat, which is a genus G Riemann surface with n orbifold points Q1 to Qn. It turns out the Seifert vibration is fully determined by the so-called Seifert symbols. So we can write any Seifert compact Seifert manifold in terms of a degree of the circle bundle, a genus G of the underlying Riemann surface, and then n tuples Qi Pi, which are the Seifert invariants of the manifold. And these are the invariants of the exceptional fibers over the orbifold points. So these points have some local neighborhood that looks like C mod set Qi. And then these Seifert fibers can be obtained by Dehn surgery or at the orbifold point. So you can in a sense imagine that we take some cap, and using the surgery we using a Dehn surgery with a prescribed SL2Z twist, we can glue it back on. And this SL2Z twist depends on the Qi Pi of the fiber. Now for a theory, say Chern-Simons theory, based on a simply connected group, the off-shell Seifert fibering operator that does that job is a sum over orbifold or fractional fluxes, which has been computed in this paper in full generality for any n equal to 2 theory. So it takes some form for given QP fiber as a sum over these fractional fluxes n, which are in this Q-reduced magnetic wave lattice for G tilde. And then the thing we sum over for fixed fractional flux is a complicated function, but it's completely known. So it has some contributions, say, from gravitational Chern-Simons action for the Chern-Simons action of the gauge group, and also from W boson in case we have a non-abelian gauge group. And with all of this combined, the supersymmetric partition function of G tilde theory on Seifert manifolds takes this form as an just the insertion of this fibering operator, which is just the usual partition function on sigma G. But then we have also a product over all these fibering operators. Now, how what we need to look at is how the gauging on Seifert manifold looks like. So we want to prescribe what is the insertion of arbitrary topological lines for gamma 0. We really need to only focus on the orbifold points because the other insertions we have looked at before. So if omega is some small one cycle wrapping the orbifold point at the base of a QP fiber, then a line wrapping this orbifold points acts on the bit evacua as follows. So it really just shifts this factor in this way, and you can essentially see it by decomposing this circle into two lines, which look like the ordinary zero form operators. Now, summing over insertions around the given orbifold points gives us the fibering operator of the G theory. And so it takes this fibering operator for the G theory, looks like a kind of averaged function over the G tilde theory. And you can evaluate it as summing the same function here for fixed fractional fluxes, but we sum only over fractional fluxes for the G reduced magnetic wave lattice instead of the G tilde. And with this, we can write supersymmetric partition functions of the non-simply connected theory on any Seifert manifold, again as a trace over the beta vacua of the gauge theory. So as before, the beta vacua are just labeled by orbits together with their stabilizer group. And this partition function just takes the form again as a sum over beta vacua of the Handel-Klingler operator of the G theory times a product over the Seifert fibering operators of the G theory. We can show that this arises in the A model by summing over all topological symmetry operators for the zero form symmetry and the one form symmetry on the orbifold Riemann surface. So we want to sum over all possible insertions, which is given by insertion along the S1, which is labeled by this delta here. And then we have here insertions along the 2G ordinary cycles on the genus G Riemann surface and the n+1 orbifold points. And we can show that this side here just reproduces the first line. And then as before, we can, for example, for SUN, we can massage this sum further for SUN or for PSUN, where we gauge the set N. And so, for example, partition function of the PSUN theory for an arbitrary Seifert manifolds, it's just given by what we had before, times a product over the PSUN Seifert fibering operators, as before, where it was before the SUN fibering operators. And so, for example, if we have these fractional fluxes for SU, say for SU2, if they are say just the integer lattice, then the PSU2 or say SO3 fractional fluxes, that would be a finer lattice. So it would be, for example, the half integer points. And again, we can generalize these two subgroups, two gauging subgroups of set N. Maybe I can finish on this with this slide here. So one example we can, for example, look at are the torus bundles. So they are interesting examples. They are non-trivial vibrations of the torus over the circle, where we have some interval times a torus, but then we glue the endpoints of the interval by giving the torus a SL2 set twist. Now we can identifying the interval with the time direction. the axioms of TQFT express the partition function on that torus bundle as a trace, which is just the trace over the representation curly A of the SL2 set matrix A on the torus Hilbert space. And the reason why that's relevant is that there are up to conjugation exactly 5 torus bundles that admit a Seifert vibration, which includes the trivial vibration, which is just the 3 torus. And they are the ones which are twisted by the SL2 set element C equal to -1, and then these 3 elements here. And so, for example, the C-twisted partition function is interesting because it gives the trace, according to this formula here, of the charge conjugation matrix. So it interchanges representations with their complex conjugate representations. And so it counts the number of self-conjugate representations. So, for example, for SUN with n odd, we can simply compute, or we can simply count the number of self-conjugate representations, which gives this partition function here. I guess I should stop very soon. Should I? Do I get 2-3 more minutes? Or
you can take a few more minutes. Yes.
Okay, thanks. I think I just have 1 or 2 more slides actually. And so maybe also one check that I wanted to mention is that this formalism allows to compute many different partition functions for groups that just differ by their global form. And so one important check is actually what happens if the gauging in a sense is not doing anything. So, for example, in 3 dimensions, the background fields we want to sum over when we compute the gauging, there would be valued in this H2 valued in gamma. But in many cases, that group is trivial. And so the gauging in 3 dimensions is just the trivial operations because we cannot sum over background fields. But in the A model, actually turns out that the gauging is never a trivial operations because we can at least always consider a sum, or we can include always line operators on the extra circle. The partition function of the G and the G tilde theory in these cases actually turns out to differ by a factor of the order of the group. And now these cases when the homology or cohomology is trivial can be realized in 2 quite different ways. Either the homology is trivial, the integral homology is trivial, and so that means that the gauging is trivial for any possible subgroups we want to gauge, or the homology is trivial only for a specific choice of gamma. And just concerning the first case, so we can consider the manifolds here, which have genus and degree 0, and just an arbitrary number of Seifert fibers. These have trivial integral homology if the QI's, PI's satisfy this equation here. And we actually find that this equation here is satisfied whenever the equation 2 here is holds for all orbits omega. And we also conjecture that H1 being trivial always implies this relation. And why that's perhaps surprising is that it just looks like it could be the same, but we're just swapping the sum and the product. For SUN, Chern-Simons, for example, we check this relation in many cases, and it turns out to hold for the cases that it should. So, for example, we can look at these spherical manifolds, which are these Seifert vibrations, where the second equation here holds if and only if the homology is trivial. And so the homology in this case is trivial if and only if capital N is co-prime with or is co-prime with 6 minus M. So yeah, just to conclude, I gave some general description of 2D zero form symmetry and 1 form symmetries in the 3D A model, including anomalies. I discussed the extension of the A model formalism to non-simply connected gauge groups. This includes the computation of partition functions of 3D n equal to 2 theories on compact Seifert three-manifolds for essentially any gauge group. This includes the Witten index and topologically twisted index, and also partition functions for on other manifolds such as printable bundles, length spaces, squashed three spheres, homology spheres, torus bundles, and so on. And finally, I showed how the 2D gauging matches with the anyon condensation for pure Chern-Simons theory. So I think that's I should stop here. I'll just show the last slide.
Okay, let's thank Elias. Do we have questions? So I can start with did you consider also some matter in the theories or just pure gauge theories?
We made some comments in the papers about matter. I guess we noticed that even just pure Chern-Simons is already very rich.
Yeah.
But of course, it's it would be very interesting to study in much more detail the theories with matter.
Of course, like if you now add matter, it could screen some of the symmetries or this. But modulo this, does it make the problem much harder to address, or is it essentially the same? You just like start with something different. Like, are there big problems that come by including some fermions, some chirals?
Yeah, I guess as long as the one-form symmetry is or the matter is invariant under one-form symmetry, so you could include adjoint matter. I think the whole story will not be affected. So the main part of the talk was this section or this the second part, I guess. I think that was not necessarily assuming pure Chern-Simons. That could be any 3D n equal to 2 theory.
Because I mean, from my point of view, at least 3D in this 4, typically, if you add a little bit of matter, everything gets a lot easier. Like more like somehow, yeah. If you add enough stuff, then everything becomes simpler. But so I was wondering whether maybe there's something similar here that. But maybe not.
Yeah, I guess what is very nice about pure Chern-Simons is essentially that finding the bit evacuates is quite straightforward, just in terms of these representations, and I guess that becomes a bit more complicated once you add matter. But then, yeah, it would be interesting to study this in more detail for more generic Chern-Simons matter theory.
Okay, do we have more questions? Okay, and if not, I would say let's thank Elias again, and we can go off the record.